So let's go with a theory. So now I'm going to have to be very vague since we're going through the first example, so I'm going to skip over a lot of stuff to be able to have a context when we talk about. But a friend says they run a 5-minute mile, and you don't think he's that fast. So we've got a concept here. Just based off of that very first sentence, I can be able to define my what? And I can define my null and alternative hypothesis based off that one statement. I'm not going to have you write all of this, but I'm going to do an example that goes through all this whole time. Just write that first sentence so that you have something in your notes that's context. So a friend says he runs a 5-minute mile, but you don't think he's that fast. So now realistically, is every single time this person goes and runs a mile the exact same scenario? No, he might have not eaten, he might have eaten a whole lot, it might be pouring down rain, it might be still every scenario is not the exact same, so there might be external factors. We're kind of pushing away from considering all of that right now just for the sake of having one to talk about. So let's go ahead and write that as a null and alternative hypothesis. So H sub 0. I'm going out on a limb a little bit here, but which do you think is my parameter that I'm trying to deal with this problem? Which makes more sense? Mu. Now, just like chapter 8, did you have problems with if it was a mean or a proportion problem? No. Am I being extremely vague here? Yes. So on the test, I'll be more specific that we're dealing with average, but I think y'all can follow that. What has to go here?
Equal.
And then mu equals,
5.
and what do you think should also be there?
Units.
So we want to have our units there. So I can also write, what does this start with? H what? H sub A. What is it here? 5 minutes also stays the same. So every time you do one of these, this is kind of how I think through it. I don't even have to think, I go ahead and write those. My only decision was here. So this one is a little bit weird with, no, I guess this one's fine. Because if he's not that fast, we think he's what? We think this is going to be greater than. Sometimes when I do stuff with running, first place means a lower number, and that gets to double negative almost, but I don't have to deal with that here. All right, so that part, context, we can kind of connect there. So this is where I said I'm going to use a bunch of hypothetical stuff. No, I don't want you to write all this out, but conversation-wise, I kind of need to have it. Let's say that it is known, that his mile times overall are fairly normally distributed. That's really not that unlikely to think of. He's got some bad days, he's got some good days. Most of them are fairly consistent. That's probably going to be fairly symmetrical anyway. Why do you think I needed to state that? So that we can use normal approximation. I would just write his mile times are fairly normally distributed. So write that down. Just write that his mile times fairly normally distributed. Now this next one, hoping y'all are good with this. Let's say that we know his mile times vary by an average of 0.25 minutes. What am I trying to get at there? Standard deviation, because standard deviation is average distance from the mean. I didn't say mean there, but I should have said average vary from minutes by an average of 0.25. So we're writing stuff down. Instead of writing all that down, what can I write instead? Sigma equals 0.25 minutes. So you needed this, and then sigma equals 0.25 minutes. And I made it easier to just deal with, instead of like dealing with seconds and stuff like that, we're just gonna keep it all minutes, make it easy. And then let's pretend that mile times are independent. We just talked about that. Conditions might be different, but for the sake of our problem, we're just gonna pretend like they're all the same. All right, so let's think about making one of these, so making a distribution for what he said. I don't want you to draw anything yet. I want to draw a distribution. What's it going to look like? Where do I start? We do from what we just wrote down. I got to start drawing. What do I draw? Okay. What do I know about that? Okay. This whole distribution is sarcastically saying we believe him. What does he say? The middle is 5 minutes. That was his claim, so we're going to say, okay, we're going to go with that. What else do we know about this distribution? It's normal. This is like a kind of more like a tip than anything else. There is always a point in your graph, which this part is technically calculus, but so like here, if this part of the graphic goes this way and this part of the graphic goes this way, right? There's a point where it switches, which is probably like in here-ish. Technically, that is where your standard deviation is. But like I said, that's kind of a nitpicky thing. But it's sometimes nice to know because sometimes on the AP exam, if they give you one that's drawn, you can look at it and figure stuff out without having to do a lot more math. So what would I write here? And then 5.25, 5.5, 5.75. So just kind of a refresh and thinking through this. What percent would fall between here and here? 60, 68 plus between here and here would be what percent? 95, and 3 would be 99, 99.7. So theoretically, that's what we're going with here. So we make this whole graph based off of pretending we believe him. So now that we have gotten this all drawn out, go ahead and draw this and write based on his claim. All right, so let's say it runs once, and y'all don't have to write what I'm writing. We'll make something easy right now. So I want you to shorthand that Just say he runs 5.25 mile. So we want to think about how possible is it that he does that bad just by chance? I imagine you can be with me enough to feel good about that without having to do the same thing. But if I'm saying now, what's the likelihood that he does that at least that bad? What do I mean by at least that bad? Here or where? Well, just based off of empirical rule, from here to here was 68%. What percent is this going to be? Math here. 68% between here and here, right? Go with me that. Which means how much total is in both of these?
16.
32, so how much is just in one? So this is about 16% here. So the likelihood that he just happened to do that bad when he really runs a 5-minute mile, there's about a 16% chance. Would we feel good about telling him there's no way that's possible, you're completely wrong, if that only happens 16% of the time? No, that could happen. Like 16% of the time, yeah, we don't expect it to happen every time, but that's nothing I would take somebody to court over. It's going to happen 16% of the time, so that's okay. So this is the idea that we're going with. All right, now let's think about the fact that we make him run multiple times. All right, so let's say he runs we'll do easy, twice. So 5.25. We'll make it really easy. Let's say he runs that twice. Would I want to draw this on this same curve? No, why? So let's think about if I wanted to write this one as a problem. So this is from like chapters ago. I would write this as P parentheses what? Right? So how is this one going to be different than that? Is this just an X? So I would do what with it? I just made it super easy to make them the exact same number. Like if this was 5.25, this is 5.75, what do you think I would do with them? Y'all are thinking way too hard if you don't listen. What? Average them. So this is a P parentheses X problem. This is a P parentheses what? X bar. So do you see the difference between the two? All right, so let's think about this one that way. So his claim is mu of X bar, which equals what? Think about it just like we did this a couple chapters ago. And his claim was what? What about this? And so I'm going to write symbols first just so that we're all on the same page. Symbols wise, what's my equation for this? So that was 0.25 over, this would be square root of what? I don't know what that is. Type that gives me the 4 decimals. Now, what do we always have to do when we do this one? And I'm going to shorthand this a little bit because y'all are good with this. I can go through this whole process without showing my work. What am I actually saying in context by 10% condition? So my n is what? My lowercase n is what? 2. What do I do with 2? Multiply by 10. So I'm saying, what about 20? He can run, has run, will run at least 20 times. We're good there? All right, so that gives me my center. This gives me my what? What? What have I not talked about? Well, what do I know? So you can use one approximation. All right, so now I'm going to draw my curve, but I'm not necessarily going to draw everything out as perfect. What's going to stay the same other than just the fact that it's a normal curve? So it looks like that. Now what's another thing that stays the same? Center's still 5. But now what? So this is going to be like 1 point, I'm just going to go this direction, 5.1768. And then one more would be 5.35. I'm not going to know. 6, 13, 535, 13. Oh, I said that. I put it in the set. Yes, okay. So where would 5.25 fall? Somewhere between them, right? So now our line is going to be somewhere in here. But we're still testing that we think he's slower than that. So we're still testing that way. Now, I want you to understand that this graph that I'm drawing out right now, I need you to understand this. But once I get to the end of the today, your graph is going to look a lot different than this because we're going to think through this process and make it a lot shorter. So what I'm going to erase where I wrote 5.25 just for now. Five is in terms of my context, but that middle line can also be written as what? If I didn't write these numbers down here, I could write different kind of numbers. What other kind of numbers go down here? What? My z's. What goes here? Which means this would be, and this would be. So my z is somewhere between 1 and 2. Like that makes sense. But where exactly is my z? Do you think that's going to be hard to figure out? What's my equation for z equals? Words, not symbols. What is my value for this problem? 5.25. What is my mean for this problem? What is my standard deviation for this problem? 0.1768. And why is our value 5.25. And maybe I shouldn't have used one that was so easy. Maybe I should have done that as 2 that had average for that.
So it would be your X bar would be your
Mm-hmm. So now I want you to write this as test statistic equals what we're finding is Z, and I'll explain why. So our value is our X bar. What's my symbol for mean? U of X bar. What's my symbol for standard deviation? Sigma of X bar. Well, so this makes it really easy because I've already found this, I've already found this, I've already found this. What is my X bar for this problem? What is my mean for this, mu of X bar for this problem? What is my sigma of X bar? Type that in. I should definitely get an answer that's between what and what. 1 and 2. We just went through and figured that out. And what do you get? So we're doing it as a Z. So usually how many decimals do we go through Z? 2. So 1.4 what? So this part right here, you will not actually draw out that way on a test. You'll do it from here. So like we'll go U of X bar, sigma of X bar, check our conditions, and this is essentially like do. So from here, now I'm going to do it like it's a problem back from chapter 6. I draw my line at 1.14. Now we know that we're shading to the right because our last 2 pictures we shaded to the right. But what in this problem actually tells me that I shade to the right? Where did we start with this problem? So this right here tells us where to shade. And now if I look up 1.41, my Z table, so when Z is 1.41, we get an area of what? But I want to do what with that? Which gives me, so just like the way we talked about this last problem, what does that 0.0793 actually mean to me? Context. There's a 7.93% chance that he would have actually had these 2 running times if his claim were what it was. Does that seem like it's terrible? I mean, maybe, maybe not. We're going to get to a point where we decide before we start a problem what we think is good enough to say that it's not.